Hello, my name is Ariana Islam, and this is my video lab report for the second physics lab for Physics 2212, the line charges. And so the introduction and purpose of this lab is to investigate charge polarizations and electric forces with the tape, similar to Lab 1. However, we're using the results from Lab 1 to more accurately model the charges as distributed charges on a rod, and my preview is that I found that the electric force was about 2 times 10 to the negative 3 newtons, and then the gravitational force was about 2.2 times 10 to the negative 3 newtons, and that the charge was about twice the result that we found in the first lab. So the fundamentals and models we're going to be using in this lab is Coulomb's law, where K it's equal to K times the charges over the radius squared, similar to what we did in the first lab, just to calculate the amount of charge on there. And then we also need to know the electric field of distributed charges on a rod, and the way we calculate this is simply splitting up the rod into point charges, calculating the electric field for each point charge, and then using superposition to add each piece of electric field to find the total electric field of the distributed charges on the rod. And we're going to be using this in order to model the charges on the tape for this lab, and in order to find out the piece of charge that is on a single piece of U-tape. And then of course we also need to know that Newton's second law, F net equals 0 and F equals ma, so that way we're able to set the y components equal to each other. The electric force should be canceling out the gravitational force. Now, in order to do this lab, we do need to make some assumptions. The first of which is that the charges are evenly distributed along the tape. This will allow us to calculate E using the distributed method. We also have to assume air resistance is ignored to simplify our force calculations to make sure that the only things acting in the y components are the electric force and the gravitational force. And then finally, we need to assume that both types have the same charge, so that way we can calculate the electric field. Now the experiment is the exact same as it was in the first lab. The system is the pieces of tape, the surroundings is basically everything else, and then the initial conditions for the experiment is the base tape on the desk, and then extra tape in order to make U-tape. And so the procedure was to create U-tape by quickly pulling out a second piece of tape over the base tape, and then observing how the U-tapes can make each other float by suspending one U-tape on two objects as a bridge, and then holding the second U-tape nearby so that they would repel. Now, in order to calculate everything, we have the code. The first part is the exact same as the first lab, all of the constants. At the bottom is just the function in order to calculate electric field, which of course we're going to need. And then here in this slide, you can see that the first function over here is just creating the line of the point charges, so it's basically modeling the tapes. And then here at the bottom, you can see that we have made both the top and the bottom tape with the line charge function. So that way we're just modeling it as distributed charges on a rod. And then finally here we basically have the scalars, and then this loop right here is just basically calculating the electric field for each piece of tape, or sorry, for each charge that's in the tape. And then we just make all of the arrows. So for example, we make the arrow for the force and the gravitational vector, and then we just calculate the electric force on both of the tapes. And you can see the results here. The arrows are basically equal, representing the electric force pointing up and gravity down. The red and blue dots are all of the charges that are on the tape, and then the green arrows are the net electric field. And then, seen here on the bottom, it's displaying the gravitational and electric force. Now, the discussion here is that the line charge calculations for this lab are much more accurate than the point charge calculations because it's a simple method of basically just taking more exact measurements. However, the electric force and gravitational force were not exactly equal as theorized, but they were still very close. And of course, this is probably due to some other factors that weren't accounted for, such as air resistance. And then some errors that could have been prevented on this lab is that the charges may not have been evenly distributed on the tape, which would mess up the calculations a little bit in the coding. And then, of course, the charges on the two tapes might not be equal due to the human handling disrupting the charges, as we discussed in the first lab. And then, of course, only two forces were considered in the y direction, so any outside components may have caused the gravitational and electric forces to not be equal. And then, of course, for the discussion questions at the end, what if you had modeled each of your charges as a single point charge like in the previous lab? The charge calculation would be more inaccurate since it's a simplification of what's truly happening. The charge found in lab 1 was about 1.3 times 10 to the negative 8 coulombs, and the charge found in lab 2 is about twice that. And why do these estimates differ, and which one is more likely to be closer to the real value? These estimates differ because of the two models used to calculate them. One of them is a single point charge, and the other of them calculated by superposition for a distributed charge. The model used in this lab, the distributed charge, is much more accurate to the real world value since the charges do not accumulate in one point in real life but rather spread out like they do in this model. So the more pieces that you split the rod up to, and then sum up or integrate as we do in class, the more accurate the calculation will be. So the more this code just splits it up, the more accurate our lab will be. Thank you for your time.